Good afternoon, ladies and gentlemen. Welcome to this video on how to answer these exam questions based on drawing derivatives. I am ready. Have a cup of coffee. Let's smash them out. Once again, please don't watch this entire thing. Skip to the question you are stuck on, and hopefully me explaining it will help you. Otherwise, by all means, chase me up in school and we can go through it again in a different way. Alright, what people find the most difficult about these questions is the inexact nature of their answers. Therefore, the answer that I give won't necessarily be exactly the same as the official answer, but the important thing is to get the main features right and they will earn you the marks. So, let's get stuck in. Y equals f of x is shown below. Cool, we have a cubic. Clearly mark and label a point where the derivative is 0. Alright, so the derivative is 0 can happen at two places. It happens either here or here. Pick one, doesn't matter. Mark and label a point B where the derivative is greater than 0. So the derivative, remember, is the slope. Greater than 0 means it's positive. You can go anywhere here for B. I wouldn't go too near the turning point. I wouldn't actually go near here just in case the examiner tries to think you're going on the axis, even though technically you'd be right. Just go clearly somewhere up there. Clearly mark and label on a point C where the graph itself is less than 0 and the second derivative is greater than 0. Just a quick reminder, second derivative greater than 0 means it's concave up. So if we want concave up and below, we can go C here, or actually anywhere along there, as long as we are under the x-axis. Alright, moving on. Graphs, the initial, the derivative, and the second derivative are shown below. So, what we have is to identify one of each of them, or which is which. I can see that when this one turns, this one's equal to 0. And I know that relationship. That gives me to suspect that that's f of x, and this is f dash x. Now let's see if we can identify this one. Well, it's the third one remaining, so presumably it's double dash, but we can check that. We can see that C looks a bit like an inflection point. It goes from concave down to concave up at that C. And where the inflection point occurs is when the second derivative is equal to 0. That works out nicely for us. Also, it's where the first derivative is turning. So, match done above. Let me just pause and shut my door. Alright, what is special about points A and C? Well, point C is a non-stationary inflection point. Non-stationary inflection point, meaning it's not flat, but we are changing from concave down to concave up, making an inflection point. Part A is a turning point or a stationary point of the first derivative. Alright, question 4. Now, question 4 we haven't covered yet. It's not in this current stat. So, don't stress this bit, but I'll answer it anyway for you. Basically, the derivative is a way of finding the area under a curve between 0 and 1. That would be awfully shady graphical representation of that. Which of the following graphs on the page above where is it? Explain your answer. Alright. It's this one, but I'm going to skip the explanation in the interest of time. Alright. For the graph y equals h of x, x is greater than 0, shown below. Gradient of the chord BD represents the average rate of change between B and D. Alright. For a second chord that more closely approximates h dash x. Alright. Must also go through D. So, I would go CD. I'm going to drag that into place. There. Point A on the graph above is an inflection point. Alright, so that's an inflection point. on the axis below, draw a graph that shows the shape of h dash x between h and x. Alright, so first one of drawing derivatives. Now, if you're drawing derivatives and there's no scale here, everyone's answer is going to be slightly similar, but also slightly different. The important thing is to get the key features the same. One way to get the key features the same is I would draw a graph of x values. So I would almost start just below A, B, C, D, E, F. And then I'm going to take an estimate of what the slope is at that point. And if I estimate the gradient or the slope, that will give me a value for f dash x. Because remember on this graph here, y equals h dash x. This is that value here. So if at a minus 1, like here, that slope might be 1, because it's going there, 1 across, 1 up. It's positive, it's not too steep, 1. That's here. Here, though, it's steeper. We could call it 2. And B, it's less steep, say 1. Now, what's interesting to note is this here is an inflection point. Inflection points occur at either the max or a min of a first derivative. Note, when it goes from 1 to 2 to 1 and it's going to keep going down, this will be a max. Oh, I've shifted them all off 1, sorry, haven't I? 1, 2. Let me just reset this table. Resetting. X, A take 1. The slope is 1. A, the slope is 2. B, the slope is back to 1. So this will be a max. C, D, E, F. Good if I knew my alphabet. Alright? If I'm saying the slope at B is 1, the slope at C is still positive, but it's less. The slope at D is still positive, but it's less. The slope at F, don't ask me why we skip E. The slope at F is still positive, but it's less again. We're almost flat. So what's going to happen is we're going to start low at 1, go up to 1, back down to 1, and slope off like that. And that's the shape we're looking for. And by assigning values to the approximate slope, we can see that that would be our shape. So, in line with A, we want that to be the maximum, and by F, we want to be down at a quarter, or like an eighth even. We're going really low. So from here, I would have it going up, peaking there, and dropping off. Maybe even a little smoother than that. Up, peaking, and dropping off. Up. Oh, goodness. If. It's worth 3 marks. You're going to get 3 from one thing. You're probably going to get 1 from recognizing that you're going up. 1 there. 1 from getting the peak right, and 1 from clearly asymptoting at the bottom here, which I probably haven't done as well. If anything, you could probably just do this, couldn't you? There, that asymptote is much better. And there will be your 3 marks. Alright, onwards. Here you're given the derivative. So, the derivative on this axis, if it's a derivative, it tells you the slope of the original function. So what's happening is I would do this again. X, slope. 0, 1, 2, 3, 4, 5, 6. And when you're answering questions like this, you don't necessarily have to do this table, and certainly it doesn't form part of your answer. It just helps part of your work, and you can do it on scrap paper off to one side. Alright, I'm going to call this here minus 1 as a starting point. So the slope at 0 is negative. By here you're -2, by here you're -3, by here you're -4. So we're getting very steep and negative, and then we head back towards positive again. Sorry, what was happening? All right, 3, we're down here at -4, -3, -2, -1. So basically, the slope starts off not very steep, but still down, drops to very, very, very steep at 3, and then goes not very steep again, but still down. So we're starting off relatively flat, dropping off steeply, and going down. We're getting that S-bend happening there. Note that the slope is always negative. The reason the slope is always negative is because this is always below the x-axis. Alright, on the x below, sketch a graph of the original function. So we've got the original function slope up above. It's negative, gets more negative, more negative, more negative, less negative, less negative, less negative. So at 3, and I'd be marking a line in here with a pencil or something, that is going to be my steepest part. So starting, say, here, it's going to be negative, steeper, and less negative. Thing is, I have to go through B, so let's try that again. You'd think I'd be able to hit B. The point is, I'm going very steep here, which is not actually what I've drawn. So I'm going to make this very, very steep, and then connect lines to it. Alright, it's difficult on a computer screen. I can hear you all laughing. Alright, there. It is the steepest there, less steep, and flattening off, perhaps not flattening off that much. We're still in negative territory and going down. Here would be the key to it. Note that as it appears to be asymptoting to the flat here, it would appear to asymptote to the flat here. Not necessarily the flat on the x-axis, but just flat. Alrighty. Consider the function f of x. The sign diagrams of those two are below. Alright, so what this means is the slope is positive, we're going up, the slope is negative, and the slope is negative. This means that we're concave down, concave up, concave down. The points A, B, and C are on the curve. Sketch the graph. Alright, so we want to go up to start with, and then at 2 we want to peak. -2 we want to peak. Alright, so let's call A our peak. Up, and peaking it at A. Now 1, we're going from concave down to concave up, meaning there's an inflection point there. So here is an inflection point. We want to go from concave down to concave up at B. So we're going to hunt down to B, and doing this computer is really hard. We have that. Then this is concave up. But no, the line doesn't go up because the slope is still negative. So it's going negative and negative. What's happening though is at 4, it is going to be flat instantaneously, but the slope is negative either side like that. So we are going to go, I might even do this better. Oh, glorious. That's my best one yet. Alright, so key features. Positive. Then for the rest of the graph, the slope is negative. And that's what the first derivative showed. Positive, rest of the graph, it's negative. Second derivative, we are negative until 1. Negative until 1. Then we are positive, concave up, negative, negative. And getting those 3 features right is absolutely all you need. Details like what exactly is happening on this end aren't hugely important. All you know is the slope is positive. What's happening afterwards on this end, again, you don't know. So don't stress those little details. The important thing is you get the main features right. Alright, points A, B, C, D with coordinates, x coordinates A, B, C, D, E, are stationary points and inflection points on the graph. A fifth order polynomial is shown below. Alright, which of the graphs are stationary points? Alright, stationary points are when f dash x equals 0, meaning the instantaneous slope is 0, and that is A, C, and E. Those 3 points, the slope is equal to 0. Which of the points are points of inflection? So points of inflection are where we turn from that to that, or that to that. Points of inflection are B, C, D. You can see how it goes from concave down to concave up to concave down to concave up. So B, C, D. B, C, D. Hence draw sine diagrams for them. Alright. So for the first derivative, it's positive when the slope is positive. So it is positive there. So if we put A here, it will be positive there. At B, the first derivative is still negative. At C, it's equal to 0. So C, negative. Note that I'm not plotting B in there because according to the first derivative, nothing special happens at B. It just changes over. At C, we're equal to 0. And at E, we're equal to 0. Negative, positive. So note, these are the key points on the sine diagram. Alright, perhaps similarly, BCD. So we can probably guess that we're going to put BCD there. But here, it's concave down until B, so it's negative. So we're going to put B here, negative. C. Between B and C, the slope's like that, so it's positive. After C, we go down to D, negative. After D, we are happy again, so positive. Sweet. Right. Consider the graph y equals f of x shown below. Okay, the graph has a non-stationary inflection point at 2, 0. So there, it has no other inflection points and no stationary points. It has vertical asymptotes at x equals 0 and x equals 4. Nice. For what values of x is the function increasing? Alright, so the function is increasing from 0 up to but not including 4. And in fact, we have an asymptote at 0, so it would be 0, x, 4. It's those values there when the function is getting larger as we go here. Over here, the function is not increasing. What value of x is the second derivative less than 0? What values of x? Alright, second derivative is less than 0 when the graph looks like that. So when does it look like that? Well, it looks like that here. And actually, it doesn't look like that again. So we are looking at between 0 up to and equal to 2. Actually, no, it's strictly less than, so just up to 2. So 0, x, 2. On the graph below, sketch the value of the derivative. Alright, so here I would do this. Zero, 1, 2, 3, 4, 5, 6, 7, 8. Alright. Now, it's a matter of picking off values. Noting that at 4 it's going to be undefined. To start off with, technically 0 it's undefined, but very close to 0, the slope is going to be extremely positive, like 100. By the time we get to 1, the slope is still pretty positive. It's like, I don't know, 3. Here, the slope is not 0, but the slope is positive. It's like, I don't know, 1. Then it gets steep again. By the time we're at 3, we're getting steeper again. 3, and then close to 4, we go up to 100 again, and then at actually 4, it's NA. Jumping over to 5, well, it's minus 100 because it's extremely steep down. And by the time we get to 6, or actually minus 5 is minus 1, and then by the time we get to 6, we're minus a half, and then by the time we get to 7, we're minus a quarter and minus an eighth. Note that there's a dot on the end, so it doesn't continue on forever, we just end. And we're ending slightly negative. So, on a scrap piece of paper, you would have done this. I'm going to drag it down here. I have no idea where this went. There. Alright, and let's use this. What that means is that we are starting extremely high, going down, down, up, stopping, jumping to negative infinity. Alright, so let's try. We are starting extremely high, dropping to a minimum at 2, going up, like that. And then from here, the slope goes there to there. Arrows on the end, arrows on the end, and a dot on the end here. Note how these ones had arrows. If they have arrows, our derivatives need arrows. So note how it goes extremely positive to extremely negative either side of the asymptote. It goes extremely positive to extremely negative either side of that asymptote. At 2, we're told there's an inflection point. The inflection point of the original graph will be the minimum or maximum of the derivative. And note there's a dot there. And basically, those 4 things I've highlighted are where your marks are coming from. Fun. 4 marks. Again, this bit here is not part of the marks. It's just a tool that helps you graph. Alright, question 7. Consider the graph y equals f of x as drawn below. So we've got the original graph. The graph has 1 stationary point at the point x equals 0, and 2 inflection points at the point x equals 0 and x equals 0.874 random. But we assume that's like there. Sure. So we are talking stationary inflection, regular inflection-ish. Cool. Tick the box, the appropriate box to indicate which of the following statements is true for f-x for all values. Alright, f-x is greater than 0 for all values of x. No, it's not greater than 0. The slope is negative entirely. F-x is greater than or equal to 0. No, is less than 0. Not really, because here f-x is equal to 0. Which leads me to tick that. F-x, positive, negative, and 0 values. Well, I don't see a positive one there, so it's not that. Cool. On the axis below, sketch the graph for f-x. Alright. You can probably see where I'm going with this. X slope, which is f-x. Cool. Now, the axes here are a little messy. -1, minus 0.75, minus 0.5, minus 0.25, 0, 0.25, 0.5. Let's jump a bit, 0.7, no point. Might as well include their official point, 83, whatever it was. Then 1, 1.5. Alright, it's an absolute mess. But remember, you're doing this on scrap paper. It doesn't have to be part of the actual formal answer. It's just a tool to help you work it out. Alright, the slope at -1 is pretty steep and negative. Let's call it a -10. By the time we get to 0.75, it's still pretty steep. -5 at -0.5. We're starting to flatten off. It's like -2. At -0.25, it is pretty much flat. -0.5, at 0, it is flat. Then, a quarter in, -0.5, -1. Here, it gets kind of steep, -2, and then it gets less steep again, -1, -0.5. The important thing is that this, at the point 8, whatever it is, 87, it has to be the lowest value. It's the steepest on that portion. Alright? Then what we're going to do is we're going to take this, drop it down here. So this will be you using your scrap paper. And we graph. At -1, we're very, very high up here. That's a lie. We're not very high. It's -10. We're very low. So coming from low, and do we have dots? We do have a dot. Then at -0.75, we're -5. Nice. So important things, there is a 0 at the stationary point of inflection, and there is a local minimum at 0.83. So there, you're ending with dots, and the general shape is smooth. There are your 3 marks. Once again, none of the marks come from that. That's just what I use to stitch together in my head, and you're very welcome to as well. Alright, tick the appropriate box to indicate one of the statements is true for the double derivative of x. Alright, so the second derivative you find by doing the derivative of this. So we'll consider our little curve for this answer here. The derivative of x is greater than 0. Well, it's not greater than 0 the whole time because it's negative there. Not that. Is greater than 0. No, well, no, not that. Is less than 0 the entire time. No, not that. Is less than or equal to 0 the entire time. Well, no, it's that one there. It takes positive and negative values as we go through here, because we're looking for the slope of this curve. Alright, consider the function y equals f of x as shown below. The stationary points are b, d. So stationary points are b and d. Cool. Inflection points are a, c, e. Nice. Its x-intercept is the point at c and has an asymptote at y equals 0. Alright, so asymptote's off the flat there. For values of x is f of x increasing? Well, it's increasing in this portion, and it's increasing in this portion. So for x greater than or equal to 0, is it defined by 0? No, actually the graph goes on forever, doesn't it? So we don't need a lower bound here. It's just for x is less than b, it increases, and for x is greater than d, use lowercase because the lowercase is the actual values. And you can write the word and. All right. What values of x is f of x? What value is f of x decreasing most rapidly? All right, so decreasing most rapidly means the steepest negative slope, which occurs there. See. Draw the derivative. All right. Once again, our plan is to basically draw a table for these values, a, b, c, d, e, and approximate the values of the derivative. So our x values and our f dash x. If I were to say 0-ish, and then a, b, c, d, e, well, there is no f, but as it goes on, we'll write an f. All right. Just to give us some guidance. At x equals 0, the slope is pretty much equal to 0, like it's flattened off. At x equals a, it's positive. Let's call it a 1. We go up. At x equals b, the slope is 0 again. And note we're told a is an inflection point. So this is a little max there. Make a little note to yourself, it's max. C, it's negative, and it's going to be the steepest negative part. So the steepest negative part here is another min. And a b is 0, so that's a turning point. D is another 0, another turning point. E is another inflection. It's going to be positive, so it's like 1, and then it will be like positive and less positive, so then that's a max. And then F goes towards 0. Alright, so that's how we've done that in our graph paper. We grab it and we drag it down next to the graph that we're looking at. Alright, so at 0, 0, the is pretty much 0. By the time we go into A, we're at 1. I'm going to call 1 up there, and it's a maximum. By the time we're at B, maybe that's a bit high. Let's make 1 there. By the time we're at B, we're at 0. And then by the time we're at C, we're at minimum. And then by the time we're at D, we're at 0. And then by the time we're at E, we're at maximum. And by the time we're at F, we're back to 0. So what we're looking for is a better job at the end there. You want your B and D to equal 0, because B and D are the turning points. You want A, C, and E, A, C, and E to be the turning points of the derivative because they are the inflection points. For a Sine diagram for the second derivative. Alright, Sine diagram for the second derivative. Now the second derivative, it's probably most easily seen from this, is that's going to be positive, negative, positive, negative. Our key points to include are A, E, C. And pos, neg, pos, neg. A, E, C, pos, neg, pos, neg. Pretty cool. Any question? All right. 2013, 10 years, 9 years. Displacement. All right, the displacement of a particle in meters to the right of the origin can be modeled by the function st, where t is in seconds. The stationary points of this are 1, 4, and 9. 1, 4, 9. The inflection points are 2, 4, 7.6. Okay, complete the following sine diagrams. Vt. Alright, so Vt is equal to S dash T. We basically want the sine diagram of the first derivative. So at 1, positive, negative, 0, negative, positive. So the key points we're interested in are 1, 4, and 9. And it's going to go positive, negative, negative, positive. 1, 4, 9. 1, 4, 9. Positive, negative, negative, positive. Alright, AT. AT is the second derivative. The second derivative comes from recognizing periods of concavity and convexity. So concave down is negative. Concave up is positive. Concave down is negative. And the remainder is concave up. So the key points that we're interested in, I'll do in purple, are 2, 4, 7.6. Why? 2, 4, 7.6. That's a 5, 6. And the values we're looking at here are negative, positive, negative, positive. Negative, positive, negative, positive. Okay, nice. Hence, otherwise, sketch graph of Vt. Alright, so Vt is this one here. Which can also be found by doing the slope of this. So, done a few of these. I would be estimating these different x values, and the slope is going to be the velocity. So, I would do x, slope, in this case is Vt. So the slope of this function here will be the velocity of that particle. And as the x values go, I would go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, then values. Alright, you don't actually have to do numbers if you don't want, but I'll put numbers on. This one here at 0, we start off quite positive, 2. At 1, we're at 0, and then we go negative, so minus 1 for the next point in. We're still in negatives here, so 3 is not quite as steep though, it's minus a half. At 4, we're at 0. At 5, we're still minus a half. At 6, we're getting steeper, so minus 2. At 7, we're getting steeper again, minus 3. At 4, we're the most steep, minus 4. Sorry, why was it 4? 8, we're less steep again, minus 3. At let me just redo those. 7.6 minus 4, 8, 9, 10. At 8, minus 3, at 9, 0. At 10, we are going positive like 5. Alright, note a few things here. The points of inflection, there at 2, that's going to go from high. Alright, let's plot this out then. Sorry, that wasn't gloriously clear. Grab that. Drop it down here. Alright. The slope starts off quite positive. And then by time we get to 1, the slope is 0. And 2 is minus 1. 3 is minus a half. 4 is 0. 5 is minus a half. 6 is minus 2. 7 is minus 3. 7.6 is minus 4. That'll be the low point. 8 is minus 3. 9 is 0. 10 is 5. So our curve does this. Alright, so now check for arrows. We just started there and arrowed up. So dot there, arrow up. Key things to note are the intercepts. 1, 4, 9. 1, 4, 9. They're the 3 places that we were stationary. 1, 4, 9. And then the points of inflection are the turning points, 2 and 7.6. To be honest, I would be even writing in 7.6 and doing a little dashed line down here just to show the examiner you really hit that negative 7.6. Describe how the velocity changes between 7 and 8. Alright, so what happens is the velocity, which is this graph here, decreases until 7.6, and then at 7.6 increases. What this means in reality is negative means the particle is moving left. It means it moves left increasingly quickly until 7.6, and then continues moving left, but not as quickly as you go from here to there. Consider the function y equals f of x, which is shown below. Alright, there's 2 inflection points, A and B. On the graph above, mark the approximate locations of A and B. Alright, so remember, inflection points are where we go from concave up to concave down. So there is going to be one here, ish, and then there is going to be one here, ish. We are concave down, concave up, concave down. Alright, for what values of x is the graph concave? Well, it is from x is less than a, so it's everything this side, and x is greater than b, everything that side. On the axes, sketch a possible graph of the second derivative. Alright, so there are different options here, but basically this means it's negative, positive, negative. So the second derivative must go in the negatives until this point here, in the positives until this point here, and then back into the negatives. And what we could be looking at is something like this. Except I actually need to hit the point, but you know what I mean. Sine diagrams below relate to the function f of x, and its second derivative, and its first derivative. What values of x is f of x increasing? Well, it's increasing when the slope is positive. So when x is less than minus 2. There. Has 2 stationary points. Use the x-coordinates of the points A and B and classify them. Alright. Stationary points occur when f dash x equals 0. So that happens at minus 2 and 1. Minus 2 and 1. And the classification, well, this is positive, negative, negative. So what's happening is it's going up, down, flattening off, and going down again. That's that double negative, and here's the positive. So we have a max stationary point. On the axis below, sketch f of x. Alright. Well, here's a good sketch. We need to get a little more accurate than that, don't we? Alright, so minus 3 and 2. The graph goes through these 2 points. They give an indication of where the graph is. We're going to be in this region, then here, then here. Alright, so that's our 3 points. The slope is positive until minus 2. So what we're looking at is here, there will be a turning point somewhere up here. Slope is positive till minus 2, and then it is negative the rest of it. So from here, it's all downhill. We are concave down until minus 1. So we are concave down until minus 1, then positive until 1, and then negative again. So we're up, maxing there. Flattening off and heading down. That's not too bad. Alright, so let's check. We are crossing at minus 3 and 2. Minus 3 and 2, if I can hit it. That means there's a maximum minus 2. There is. There is also a stationary point of inflection at 1. There is, ish. This means concave down until minus 1. Concave down until minus 1. Concave up till 1. Concave down again. Yeah. And as these go on, we would expect arrows on the end. What I've drawn would earn you the 3 marks, ignoring the highlighter and the construction bit. But certainly while you're doing these, put them in fine pencil. Those little construction lines, little points that are going to help you guide your curve. And then draw a solid one with pencil, and afterwards erase the construction bits away. Alright, graph the curve y equals g of x. Cool. 1 second. Sorry about that. Okay, question 5. What year are we on now? 2017. Cool. Alright, the graph y equals g of x is shown below between 0 and 3. Alright, we have 2 points at 1 and 2. Points A and B lie on the curve. Point A is the only point of inflection. Alright, A is the point of inflection. Which of the following statements is true? The derivative of 1 is greater than the derivative of 2. No, it's less than. Not true, not true, true. So the point of inflection will have the steepest curve, because this is going to be positive and this will also be positive, but the steepest point will be here at the crossover between those two. Whoa. That's an exaggerated version. Justification. No. Which of the following statements is true? Take the appropriate rocks and justify your answer. The second derivative of 1 is less than 0, and the second derivative of 1 is equal to 0, second derivative. Okay, so points of inflection occur when the second derivative equals 0, and that is the justification. Which of the following statements is true? The second derivative of 2. Alright, second derivative of 2, it is concave, so that means the second derivative is negative. Concave, second derivative, negative. There's justification. That is a weird exam question. Alright. Consider the function f of x. The graph is derivative f of f dash of x shown below. Okay, so what we're looking at is the graph, the derivative. The graph intersects the x-axis at the origin and point B. At point A, there is a local maximum. Okay, so note the local maximum will be an inflection point. Complete the following table for f dash x and f double dash x. Alright, so f dash x is shown, so the sign diagram is pretty easy. It is positive there and 0 there. The second derivative at A, well, the second derivative is the slope of the first derivative, like that. on the graph below, sketch a possible graph of the first derivative that passes through the origin, clearly showing how the shape of the graph in the vicinities of x equals a and x equals b. Alright, so what this means here is the graph sine diagram is going from negative, positive to negative, so the graph will go like that at b. Here, the slope is going more and more positive, pauses and goes positive again. So what that's happening is something like this. It's non-stationary, but will go positive, positive peak. So it'll be one of these. Oh, messing this up poorly. Give me 1 second. All right, here's what I made earlier. What's happening is the slope is increasing. It reaches the maximum where it's positive. So this is the steepest portion right here. And then the slope is still positive but decreasing. Slope is still positive but decreasing. And basically we need to stitch these two together. So we are looking at this feature around A and this feature around B. A, B, B we want to max. Make it more obvious. Oh, that's a shocker. We want it starting at the origin, going very steep there, less steep, and peaking at B. All right, imagine that line P to B. Now there are lots of different ways you can do that. The key is making it obviously steep, making it obviously peak, and then with the arrows on the end. The reason it turns is because the slope goes from positive to negative. Slope positive to negative is that turn there. This crosses a B and then just keeps going down to the negatives. So this will end up going down that way as the slope continues down. All right. Oh. By now, these questions all start looking very similar, so I'm hoping you're starting to recognize patterns to them. A, B, C, D, E, F. Shut up, phone.
First, use face recognition to unlock the device.
B is local maximum, D is an inflection point, F is a local minimum. Cool. All right. For what values of x is f of x increasing? All right, it is increasing here and increasing here. So we would say x is between 0 and b, and x is, we've got an arrow on the end, greater than f. Refer to the 7 level points on the graph. Identify the properties. First derivative is positive, so we're sloping up. Second derivative negative, so in a concave bit. In a concave bit, but sloping up. Concave, sloping up, A. Sloping down, still concave. C. On the axis below, sketch f dash x. Alright, that's the original, we want the function. Once again, my favorite trick here is different x values of 0, A, B, C, D, E, F, G, and then estimate the slopes as we go through. F dash x, or the slope. So at 0, the slope is pretty positive. It's going to be like plus 2. At A, it is plus, what? 1. B is 0. C is minus 1. D is minus 2. E is minus 1. Back to 0. And F is, D. F was 0. F is back to 1. Alright, we grab that. Take it on down. Sketch it. Now, conveniently, they've put B, D, and F. B, D, and F are clearly quite important. B, it turns. F, it turns. D is that inflection point. They were all about the original. Alright, so here at 0, we're at 2. A, we're 1. B, we're 0. C, we're minus 1. D, we're minus 2. E, we're minus 1. F, we're there. G, we're 1. Alright. You want to clearly line up that D is the minimum, and you want these guys to be the intercepts, because they line up with the maxes, and that goes on. Question 6 shows graphs f of x and g of x. Cool. The graph for each function has exactly one stationary point located at 2. Okay. State the nature of the stationary point for f of x. It is a minimum. F of x does that. Figure 7 shows the Sine diagram for g of x. No, for g dash. The second derivative of it. So it is implying we're concave down, and then we're concave up. And at 6, we actually go concave down again, which is not immediately obvious, but I guess you can kind of see how it might do that, and then over. Alright, state the nature of the point located at x equals 2 from g of x. Well, since it is a stationary point, and it's an inflection point, it is a stationary inflection. On the graph, y equals f of x in figure 6 has a point of inflection at f of x has a point of inflection at 5. Alright, so f of x has a point of inflection at 5. Determines the intervals in which f dash x is increasing. Well, that's a good one. Alright, so let's think about a Sine diagram for f dash x. The Sine diagram for f dash x is going to be, it'll be negative here, 0, 2, negative. It's then going to be, well, positive the rest of the way. Determine the intervals where f dash x is increasing when the slope is getting larger. Alright, f dash x increases when f double dash x is greater than 0. The reason is this is very steep and negative, less steep and negative, less steep and negative. Throughout that entire portion, the slope is actually increasing until it gets to here. Therefore, we want x is less than 5. It is increasing. Alright, for 0 to 2, which one statement is true? Tick the appropriate box. Alright, so we're just looking at 0 to 2 in this portion here. And I can see that g of x has a positive slope the whole time, and the other one is negative. So g of x is positive, meaning it's greater than f dash x. Alright, second derivative. That is concave down, so negative, concave up, so positive. F of f double dash x is going to be higher. Good. 7. given the value f of x of g of x is increasing, which one statement is true? All right, so the graphs are being separated over 2 to 7. So now we're looking here, and we can see they are getting bigger. What that means, and this is increasing, they're both positive, but f of dash of x must be more positive because it's increasing away from g of x. F dash x is more true. Figure 8 shows the graph of f dash x. On figure 8, sketch the graph of g dash x. Alright, well, g dash x, went too far. It is positive 0 at 2, positive, positive. So the graph goes from positive down to 0, then back positive again. So g dash x is going to look something like this. It'll go positive and then positive again. It won't actually get that high. It's going to go, but make it clearly bottom out at 2. Oh, bottoming out at 2. I blame the computer screen. And that is it. We are done. Really hope you didn't watch that entire thing, but I also hope that part of it helped. Bye.